In this lecture, I'm going to discuss the implementation of floating point, which is the primary numerical representation used in engineering. I'll cover current methods and standards as well as how arithmetic operations are performed, and then conclude with one of the major challenges that we'll be facing, which is precision loss in our calculations. Let's first talk about representation. Now, basic floating point numbers are represented mathematically with the expression f equals m times b to the x. Here, the value m is known as the mantissa, b is the base, which will either be 10 in our examples or 2 in a digital system, and x is the exponent. Any floating point representation we pick will allocate a fixed number of digits or bits to both the mantissa and the exponent. The exponent x will always be an integer, and the mantissa m will be a fixed point value that is normalized, or between 1 and b, not including b. Effectively, this means that m will have a single leading digit that will be non-zero. Now, the reason for this normalization constraint is to ensure that any floating point number has a single representation in both m and x. For the next few slides, I'm going to use base 10 floating point as an example. This format isn't implemented in digital systems, but we often use it in engineering in the form of scientific notation. So consider this representation where the floating point number f is given by m times 10 to the power of an exponent x. We specify the number of digits allocated to each exponent. In this case, for m we allocate 3 digits, and for x we provide for 2. Remember that m must always be normalized, meaning that it's between 1 and 10. In other words, the maximum possible mantissa given this format is 9.99. Using these constraints, we can represent a wide range of values. This includes large numbers, such as 2,330,000, or small numbers like 233 hundred thousandths. However, if we wanted to represent a value well within the range of these two possible numbers, 2,334, this is impossible. The representation does not provide enough digits in the mantissa. The fundamental benefit of floating point is that it supports a wide dynamic range of numbers while using a simple constant representation. For example, the maximum base 10 value that we can represent with this proposed representation is 9.99 times 10 to the 99th, or, not that it matters, 9 duotrigintillion 990 untrigintillion. The smallest value that can be represented is 1 times 10 to the negative 99, which I guess is 100 untrillion-tillionths. So in short, we can represent very small and very large numbers, provided that the representable numbers have 3 significant figures. One of the side effects of this representation is that the spacing between representable numbers changes. You can plot the difference by looking at representable values on a number line. For example, if we're dealing with a 2-digit mantissa and an exponent of 2, the spacing between representable numbers will be 10. A mantissa of 1.1 translates to a floating point value of 110. The next representable number is 120 with a mantissa of 1.2 and so on. Now, if we switch to the exponent of 3 with the same representation, the spacing is now 100. A mantissa of 1.1 resolves to a floating point value of 1,100. The next representable value has a mantissa of 1.2 and resolves to a floating point value of 1,200. Now, when you look at where these values meet, there's a clear jump in the spacing between representable numbers. The spacing between adjacent values with the mantissa of 1.0 and 1.1 is 100, while the spacing of the adjacent values with the mantissa 9.8 and 9.9 is 10. Now let's discuss some implementation specifics for digital systems. As we've discussed earlier, all computers represent values using binary registers. A generalization of the binary floating point is given by the expression f equals m times 2 to the x. As in the decimal case, the mantissa and the exponent are allocated a specific number of digits, in this case binary bits. Now let's look at what the conversion looks like between a binary and decimal floating point representation. Here we'll allocate 3 bits to our mantissa and use a 2-bit exponent. Now consider the case where our mantissa is given by the binary value 1.01 and the exponent is given by 10. If we apply the binary to decimal conversion we discussed in the last lecture, the corresponding decimal values are 1.25 for the mantissa and 2 for the exponent. Plugging that into our general expression for floating point gives us 1.25 times 2 squared, or 5. Now let's look at 2 specific questions regarding this formulation. First, what's the spacing of the exponent represented by 1, 1 in binary? We calculate this by selecting 2 adjacent values for the mantissa. Since 1, 1 in binary is 3 in decimal, we'll be working with the exponent of 3 in both numbers. Here, we'll use the adjacent mantissa values of 1.00 and 1.01, which convert to the corresponding decimal values of 8 and 10. You can go ahead and check the math for yourself. The decimal spacing, given a constant exponent of 3, or 1, 1 in binary, is 2. Now, what's the largest value that we can represent with this format? We can calculate this by setting the maximum value of the mantissa, 1.11, and the maximum value for the exponent, 1, 1, and converting both to decimal and evaluating this expression, which gives us a maximum decimal value of 14. Finally, there are a couple of modifications to the generalized floating point format that real-world implementations apply. These are used to improve speed and memory efficiency, but add some additional complexity to the floating point format. In order to understand how floating point works, it's important to understand these modifications. The first is the use of an implied 1. Remember, the normalization constraint that we discussed earlier, the mantissa must be greater or equal to 1 and less than the base b, thereby requiring the first digit to be a single non-zero value. In the case of binary numbers, the only value that fits this constraint is a 1. Therefore, there's no need for us to actually store that 1 in a register. The units that perform floating point calculations simply assume that the 1 is present, so the only portion of the mantissa that's stored in registers is the fractional component. This actually provides us with 1 additional bit of precision in the mantissa, or alternatively reduces the number of bits required to store the mantissa by 1. The second modification is the addition of an exponent bias. Since our floating point values must leverage both positive and negative exponents, the most efficient representation is to always store a positive value for the exponent and apply a bias value k. The value for k will be specified in whatever floating point standard you use, and c will always be a positive integer. Now let's look at a few common floating point standards and how to leverage these features. First, in all cases, I'll stick with the IEEE 754 standard, which governs floating point arithmetic. Most processors will use this as a standard unless you're using some sort of custom system. The most common format is IEEE 32-bit, which will be used when a variable in C or C++ is allocated using the float data type. This format has 23 bits allocated to the mantissa, 8 bits to the exponent, and has a bias of 127. The next common format is IEEE 64-bit floating point, which is used in C or C++ with the double data type. This format has 52 bits allocated to the mantissa and 11 bits allocated to the exponent with a bias of 1023. One thing you'll notice if you look at the number of bits in the exponent and the corresponding bias is that the bias is generally around half of the maximum value representable with the allocated number of bits. For example, the maximum integer value supported by an 11-bit register is 2 to the 11th, or 2048. The bias is around half of this, meaning that half of the representable values are above 1 and half are below 1. Several other formats are mentioned in the IEEE standard, but are generally not implemented in hardware. The most common of these is half precision, which is available on some systems, such as NVIDIA GPUs, by using the single data type in C, C++, or CUDA. The last thing I want to discuss in this lecture is arithmetic. And my intention here isn't to describe exactly how the calculations occur in hardware, but to give you an overview of the steps that have to be taken so that you can see where potential errors arise. If we want to perform multiplication between two operands a and b, or calculate x equals a times b, we'll take the following steps, which will allow us to approximate what happens in your algorithm. First, we add the sign bits and store the result in a single sign bit for the output value x. If both sign bits are 1, the result is multiplication of two negative numbers, and adding these two sign bits and storing them in a single binary bit will result in overflow and provide the expected answer of 0, or a positive sign. Next, we add the exponents and store the result in the exponent of the output value x. Finally, we multiply the mantissa, which will likely provide a number with too many digits to fit in the allocated space in the output mantissa. Excess numbers are eliminated using standard rounding rules, which is part of the IEEE standard. Then the mantissa is adjusted, if necessary, to normalize it. In this case, no adjustments required. The final result is given by this expression, negative 3.82 times 10. Now let's take a look at addition, which will actually be more important when addressing errors. Let's add two floating point values, a and b, using a 3-digit mantissa. The first thing we're going to do is convert both numbers to use the same exponent. If the numbers have different exponents, we'll have to perform rounding and chopping to accommodate the number of registers available in the output. In this case, we'll lose the final 1 in the operand b. Now we can perform the addition. In this case, this is a subtraction since one of the numbers is negative. Finally, after performing the calculation, we normalize the result and get the final answer of negative 9.7. Now, something interesting happened here. If we perform this operation ourselves, while still leveraging 3 digits of precision in the answer, we get a more precise result, x equals negative 9.69. We can calculate the resulting error due to round off by comparing the value that we calculate with our computed result. What we see is a 0.1% error. The critical thing to note here is that we're actually getting less than 3 digits of precision in the mantissa. 3 digits of precision would have gotten us the complete result. In our calculation, rounding was actually performed during the computation, resulting in additional error embedded in the final answer. This can cause some extremely challenging problems when developing algorithms and will be a major focus of the first part of this class.